As a continuation of our last lectures for Chapter 9, we're going to focus on the 1D particle in a box model. Now, when we say a one-dimensional particle in a box, we are going to be talking about some linear chain polyene. And the reason we're using the term one-dimensional is because for all intents and purposes, this particular linear chain can be viewed as a one-dimensional box as opposed to benzene, which is then considered to be a two-dimensional box because our electron wave function can move across much of the area within the benzene ring. So for today, we will focus on the 1D box, and our example will be butadiene. So our problem today, example number 1. Calculate the difference in energy for the absorption of a photon in butadiene from the ground to first excited state. And let's recognize what butadiene is. We've got our double bonds right here. So we've got our carbon, 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 carbon bonds. If we were to write this out in this manner, we would then achieve a molecular structure that looks like this. And because of this pi conjugation along the ring, this allows our particle in a box model to be used because these delocalized pi bonding electrons are not strongly bound to the nuclei and can freely move across carbon 1, carbon 2, carbon 3, and carbon 4. So let's see how we can go ahead and apply the 1D particle in a box to butadiene and answer our question. First, you would be given a value for the length of butadiene. In this particular case, our length is 578 picometers, and remember this is our value A. 578 times 10 to the minus 12 meters. And we want to be able to calculate the number of pi electrons, and we do that by counting the number of double bonds and multiplying by 2. In this particular case, we have 2 double bonds times 2 gives us 4 pi electrons. And we need to put them in their proper quantized energy level in order to complete the problem. So let's construct our energy level diagram. Remember that energy is always on the y-axis. And we want to have individual energy levels, which we can then categorize as n equals 1, n equals 2, n equals 3, and n equals 4. In this particular case, we have 4 electrons to account for, so we're going to put spin up, spin down, spin up, spin down, and now we are in our ground state. When we talk about the absorption event, going from the ground state to the excited state, that is something similar to our HOMO to LUMO transition. And you'll recall that HOMO is highest occupied molecular orbital and LUMO is lowest unoccupied molecular orbital. And so what we're asking is, what is the energy difference between n equals 2 to n equals 3? In this particular case, we'll be using our one-dimensional particle in a box model, which is E equals h squared n squared over 8 times the mass of the electron times the length of the box squared. In the case of a two-dimensional particle in a box, we would then apply n sub z, a sub z, and n sub y, a sub y. And we are not going to do that right now, but you can imagine that this can be easily applied. Now, if we wish to find the energy difference between n equals 2 and n equals 3, you'll notice that a never changes, h squared never changes, 8's a constant, and the mass of the electron is constant. So our energy is scaling as the primary quantum number squared. And so what we're basically needing to find out is how can we go ahead and simplify this equation to make it easier for us to calculate. The first thing that we can do is apply a constant, which we'll call a, which will be equivalent to h squared over 8 times the mass of the electron times the length of the box squared. So if we were to take this information, let's draw it pictorially. Now what we know so far is that our 1D particle in a box is 578 times 10 to the minus 12 meters. We have then established some constant which can tell us about the energy of these electrons. We've got n equals 1, n equals 2, n equals 3, and n equals 4. We'll have our n values over here, and we'll have energy as a function of a over here. You'll notice that we can then just square our n values. And so the energy levels for n equals 1 is 1a. When n equals 2, this energy level is equal to 4a. n equals 3 is 9a. n equals 4 is equal to 16a. And that's because our energy is equal to a n squared. And is a simplified version that we can use. So right now, what we need to account for is this energy difference. And we can use a quick trick to figure that out and say the change in the energy is equal to a when n is squared for our first energy level, or our final energy level, which is n3, minus a, our energy level for our second quantum state, and that's also squared. And so we'll put in all of the numbers to make that more clear. So when we set up for the change in energy is going to be equal to h squared, 8 times the mass of the electron times the length of the box squared times 3 squared minus 2 squared over 1, these values being our n quantum states, and a being the length of the box. And you'll notice you only have to do this calculation once, and you'll find out that the energy is h squared, 8, times m sub e times a squared times 5, because 9 minus 4 is just equal to 5. And so this is equivalent to, the change in the energy is equal to 5a. Let's go ahead and crunch those numbers and see what kind of energy we get in joules. So that change in energy is equal to 6.626 times 10 to the minus 34 joule seconds squared over 8 times the mass of the electron, 9.108, times 10 to the minus 31 kilograms, times the length of our box, 578, times 10 to the minus 12 meters squared. We can't forget about our 5. Our 5 goes into the numerator, and once we've crunched those numbers, we get a value of approximately 9 times 10 to the minus 19 joules. Now we can go ahead and convert this into wave numbers, so let's go ahead and do that. And our value for wave numbers will be equal to our change in energy, 9 times 10 to the minus 19 joules, over Planck's constant times our speed of light in centimeters per second, and this yields a value of 45,400 wave numbers, which is very, very close, and so we'll say that this is our theoretical value. And in actuality, if we were to look at the first optical transition for butadiene, it is equal to 46,100 wave numbers and is relatively close for such a easy model to be applied. Now, if we convert our wave numbers into EV, we find out that our 45,400 wave number transition is close to 5.63 EV, which is also equivalent to 220 nanometers, and you can look up some of those conversions. 1 EV is equal to 8,065 wave numbers, and you can also use conversions for nanometers into EV. Now what I want to highlight is butadiene, which is a short chain polyene, will need a photon of 220 nanometers, or a UV photon, to excite an electron from the ground to excited state. And how do we pictorially represent? Let's go ahead, draw our energy level diagrams. N equals 1, N equals 2, N equals 3, 1A, 4A, 9A for our box of 578 times 10 to the minus 12 meters. We occupy our electrons and then have a photon come in, E equals HF, which in this case we said was equivalent to 220 nanometers, which would then photoexcite our electron into our first excited state. So this is our first excited state. This is our ground state. And if we wanted to, we can even add N equals 4, which would be our second excited state, and so on and so forth. Of course, N equals 4 would be equivalent to 16A. I can quickly calculate what the energy would be for N equals 2 to N equals 4. It's the difference between 16A and 4A, so it would be equivalent to 12A, and would therefore be a more energetic photon, shorter wavelength than 220 nanometers. So that's our application of the 1D particle in a box model. Thank you very much for your time, and we should be doing 2D particle in a box models very soon. Thank you.